Okay, so now that we have understood about the static structural analysis, what it is and where it is going to be used, now we will see how to perform the static structural analysis in Ansys Workbench. For that, we are going to take the first problem, that is of an Allen wrench. Now the dimensions of the Allen wrench are mentioned over here. You can also note it down in your notebooks so that you can also practice later on. The Allen wrench, which is of size 10 millimeter across the flats, it is stopped by a means of a 100 Newton force. You can see over here, and later it is also having a downward force of 20 Newton. Okay, and we have to determine the stress intensity in the wrench under these two loading conditions. Okay, so and the material that is going to be used for this Allen wrench is structural steel. So let us go ahead and perform this analysis in Ansys Workbench. So we will come to the software. The first thing that we will do is we will add one static structural analysis system. Okay, please rename the the name of the analysis so that you know what we have done. So I will rename the analysis. Okay, once that is done, then we will set our engineering data. So the material, we already have structural steel over here, and it is the same material that is going to be used for the Allen wrench. So I don't need to change anything over here. The next thing that we are going to do is we are going to create the geometry. Before going into the geometry, always see the type of analysis. Now the model is a 3D model, so I don't need to change the type. We are going to do a 3D analysis only. So let us enter into the geometry. Once you enter over here, you need to change your unit system. So the dimensions that are given over here are into centimeters. So I will change it into centimeters and OK. After that, create your geometry. So I have selected my plane and then I will enter into the sketching mode. I'll use a polyline. Okay, open-ended. Dimensions. Now H1 over here is of 21 units, 21 centimeters, and V2 is of 7.5 centimeters. I'll use the constraints of coincidency. Okay. After that, I also need a fillet, which is of radius 1. After setting the radius value, I'm going to apply it over here. So the design is ready. I'll come back into modeling. Now I'm going to create one more sketch on the YZ plane, sketching mode. Okay, before I come into the sketching mode, I need to set the sketch as always show so that I can see this point. YZ plane, sketching mode. Okay, so this is the point where you need to create the hexagon. So in the draw tab, we have the polygon. I need a 6-sided polygon. And I'll draw it over here. The dimensions of this polygon, you can see over here, it is 10 millimeters across the face. So I can take a dimension from this to this. Okay, you can take it as the horizontal dimension, and this is to be 10 mm. So 10 mm is nothing but 1 centimeter. The distance from here okay. Now to make sure that the center point touches over here, what we can do is we can give a dimension, horizontal dimension between this, and I can say that this is 7.5 centimeters. Once that is done, we can exit, and now we are going to use a sweep command. Okay, so the profile is going to be this, and the path is going to be this. Okay, and now we will say generate. So this is the design that we want. You can see this is the same design that we wanted. Okay, now that means the geometry that we wanted to create is ready. So let us exit from the design modeler, and now we will enter into the mechanical window. So double click on the model cell. Once you enter into the mechanical window, see your model. Okay, now check the material, whether the model that you created has the correct material. After that, we will go into the meshing. So now we need to generate the mesh. So first thing what we can do is we can generate the default meshing by using the update option. You can see that the meshing has been created. If you need to refine the mesh, you can change the relevance and create a finer mesh, or else you can come into sizing and give a definite size. Okay, so I can mention over here what is the size that you want and update the meshing again. So now you can see that the meshing has been created and it is much finer. Later you can check the number of elements and nodes. You can also check the element quality. So you can see over here what is the element quality that we have got. Okay, and we have got all hexahedral elements. That is because of the shape. Because it is a uniform shape, we have got the default mesh as hexahedral. Now once the meshing has been done, we will move on to the next option of applying the boundary conditions. For applying the boundary condition, select a static structural node from the tree outline, and then you will see in the contextual toolbar you have some options like loads, supports. First thing what we are going to do is we are going to add supports. So according to the problem over here, okay, the model is going to be fixed at this end over here. Okay, so what we will do is we will apply that condition. I will come into supports. Now you can see we have different types of supports over here. Fixed support, that means all degrees of freedom will be 0. We have displacement support, that means we will only have the translation motions over here which we can control, that is X translation, Y translation and Z translation. When you talk about remote displacement, we have all 6 degrees of freedom which you can control. We have XYZ translation, XYZ rotation. So it is up to the user whether the component has to be free or it has to be fixed. Okay. Then similarly, you have many other supports that you can use. We have cylindrical support which can only be applied on cylindrical objects. It cannot be applied on planar objects. And then we have frictionless support, we have elastic support. So these are the different types of supports that we have. Similarly, we also have loads that can be applied. So now what we are going to do is we are going to take a fixed support and I'm going to add it on the space over here. Okay. Apply. Select the face on which you want to apply the support and then say apply over here. Make sure it gets added. Again go to the static structural node and then go to node, loads. Now according to our model, we have a 20 Newton load acting on this face and a 100 Newton load acting over here. So we will go to loads and we have pressure, hydrostatic pressure, force, remote force, bearing load, bolt pretension, moments, line pressure. Different types of loads are available. Pressure will be applied on faces. Forces can be applied on lines, points. It can be applied on faces. Remote force will be a force that acts from a point. For example, it is a condition where, for example, suppose I have a plate over here, and on this plate I have a force which is acting from a certain point. It is not directly acting on the plate. There is a point at certain distance, and on that particular point the force is acting. Now because of this force, even this plate is getting affected because it is connected to that point by some other means. So the force is not directly acting on the plate, but it is acting at a point which is away from the plate. So we can make use of a remote force to create a load like this. Then we have a bearing load which will be acting on cylindrical faces and will be creating a bearing load. Okay. Then we have bolt pretension, we have moments, we have line pressure which can be used for applying UDFs on 1D elements. Okay, we will be seeing how to apply this in the next examples. Okay, so let us apply a force. So I need to apply a force of 20 newtons over here. So let us create that. I'm going to select the face and then we will give the value of 20 newtons. Look at the direction of the force acting. Okay, now I need it in the opposite direction, so I will click on direction over here and you can click over here to swap the arrow directions. Once you have the correct direction, you can say apply. If you don't want to apply the forces in the vector format, you can also use the components. Okay, and you can say, now according to our view triad, it is in the y direction, so I can say there is a 20 Newton load acting, but it is acting in the negative direction, so minus 20. And now we need one more force, so I'll again go to force, and this force I need it on the line. So I'm going to select this line and I'll say it is 100 Newton, but the direction, I need to change the direction, so I'll use this line vector and then swap it. So we have the boundary condition. You can see what are the boundary conditions that we have applied. We have a fixed support over here, we have a force of 20 newtons on face B, and we have a force of 100 newtons on this edge. Okay. Now once that is done, we will go to the solution node. Now if you see, the contextual toolbar changes. We have the result option, what solutions you want from this particular analysis. So we are interested into the stress intensity. Okay, so let us go to stress, and I will be interested into the equivalent stress. Let us say if I want the total deformation that has been created. Now you take the total deformation if you want the summation of all the deformations. But if I'm only interested into the deformation in z direction or y direction, you can go to deformation, directional deformation, and then I can say in which axis. I'm interested into the deformation in y axis, plus I'm also interested into the deformation in z axis. Okay, and I'm also interested into the strain. So these are the results which I expect from this analysis. Now after that, you can click the solution node, right click and say solve, or else you can hit the solve button over here. So now the software will solve the analysis for us. So once the analysis is completed, you will see all green color tick marks appearing over here. If there are no issues and no problems in your data, you will get the solutions. Now to check the solutions, click on the node. So the equivalent stress that is generated is 138.77 megapascal. You can see the unit over here. Total deformation that is happening over here is 3.0142 mm. Directional deformation in the y-axis is 0.013105 mm, and deformation in the z-axis is 0.0033. You can see the strain value also. Now you can see the animation of the analysis. You can go to the deformation option and see the deformation. You can also see the strain. Okay, so this is the result that we got. These are the counters. You can also increase the number of counters over here, or you can reduce it as per your requirements. You can also set the viewports if you wish to. In this particular viewport, I want to see the geometry. In this particular viewport, I want to see the meshed model. Over here, I want to see the equivalent stress, and here I want to see the total deformation. Okay, so this is for setting the viewports. Okay, so this is the analysis that we've got for an Allen wrench which is subjected to a torquing load of 10 newtons and 20 newtons in the downward direction. Okay.